there, who is extremely well trained, Cornell trained physicist. And our audience is mostly today engineers who work in fluid dynamics, and we are making small headway in communicating to engineers, which is a non-trivial achievement if you're a physicist. So it's been a great pleasure for me. So what the talk is about is a long quest which is partially inspired. It's inspired by lots of turbulence work that I've been exposed to over years, partially also Axel's work. And what is very obvious to me when you look at turbulence, and lots of other people, is that what you see are structures, and you can recognize different kinds of turbulence. So for example, when people do solar turbulence, you can just look at the picture and you can know how far you are into the sun just by looking at the patterns that you see. If you do any experiments, our graduate students can usually tell you, well, this was done at Reynolds of 814 and not 900, just by looking at the picture. Now that's extremely weird, because what's characteristic of pictures of turbulence is that you never see the same thing twice. When you see the cloud, you never see the same cloud, but we all can agree that we are looking at a cloud. So is there a mathematical way, is there a precise way of describing the vocabulary of patterns that you see? And if you can describe them, we can maybe use them. And that's the goal of talk today. And we have chosen to work in three-dimensional Navier-Stokes in the situations which you have from your own experience. So these are Reynolds numbers, which are not Reynolds numbers that you see in astrophysics of 10 to the 16. These are just Reynolds numbers rather close to onset of turbulence. So this is what you see when you open the pipe and water comes down, or if you're looking at the surface and you see some structures over the surface caused by the shear. And that's the point of the talk. And now I'll go in a particular pedagogical way. We have prepared a tutorial which doesn't use, I can see I don't need a microphone. We have prepared a tutorial which doesn't use formulas, so to make it easier for professors to understand. So, and I've been testing it by sitting behind my colleagues in fluid dynamics, and they have very short attention spans, so I've been making shorter and shorter. So if I can get a professor to go through this tutorial, I'm doing very well. So it has the slightly misleading title. It's actually, the number of dimensions is infinite. It's not 60,000, because fluids have infinitely many degrees of freedom. And we're trying to apply, why do we care about dimensions? We're trying to apply kind of dynamical systems intuition, the things that you have learned when you looked at Lorentz attractor or one of these things in low dimensions. We're trying to use the same intuitions developed there in infinite many dimensions. Now 60,000, it just says that you cannot do honest simulation of a fluid with less than 60,000 independent variables. It just cannot be done. If you do something that's smaller, you're modeling, but you're not actually computing the behavior of real fluid. So I'll show you two kinds of movies. One is I'll show you three-dimensional representations of a fluid, which are very much what you understand intuitively when you look at fluids in motion. And then I'll show you something that's new in fluid mechanics, which is to visualize the state of a fluid in an infinite dimensional state space. The original idea goes back to Eberhard Hoff in 1946. But until about 10 years ago, it was really impossible to do this because we lacked both computational experimental resources and sufficient detailed information about fluids to do it. So the stuff that I'll show you is very classical in spirit. It goes all the way back to Reynolds, but it hasn't been possible to do it until rather recently. Now, as a motivational question, why you should look at this, I would just like to show you what experiments look today. So this is an experiment, a PhD thesis from 2004 from Delft, and what's shown here is an experimental measurement of the fluid. So there is a pipe indicated by these circles, and you do three-dimensional measurement of velocity by laser sheets illuminating particles going down the fluid. Now, it's impossible for us to visualize this data. This is a terabyte of data immediately, because at every point in space you have three-dimensional velocity. So one of the visualization is to compute vorticity and then tune your vorticity in such a way that you start seeing interesting structure, and you plot isovorticity surfaces. So red means it's spinning this way, and blue it means spinning the other way. And every such experimental visualization always says the same thing. When you actually look at turbulence, it's recognizable. It has some structures, and people in fluid, engineers who actually work with fluids, give them names. So there are hairpin vortices, this and that. There's a whole zoology of these structures that you always see in boundary shear flows. There is no slip along this boundary, so the fluid is being made turbulent by shearing this way. And this is now amazing. And experiments are like this. They are as good as numerical simulations. Now you can get the same kind of data. And at this point, as a theorist, you actually have to start doing something about it. So now that's our motivation, experimental and both theoretical developments. And now a particular example for this tutorial, there are two kinds of things people compute is pipes. You send fluid down the pipe, just like I showed you this experiment, both experiments. And you shear the fluid between surfaces. So if you like to fly an airplane, you would like to know what the turbulence is close to the boundary, and these are the simplest experimental situations where you start learning about structures like that. This one is called plane couette. So there are two contour-moving planes. This one is moving away from you, this one is moving toward you. And the color scheme is like this. The red means there is a component of velocity going this way. Blue means it's going that way, and then intensity changes. Then you're not able to see inside a three-dimensional fluid. The best as a human you can do is you can look at slices of it. Gibson finds it convenient to slice it three ways. So there is a transverse slice, there is a slice in the mid-plane, and then there's a slice this way. And because this is an infinite fluid, you do it as you always do it. You put the periodic boundary conditions when you're computing it. So for example, this box is already big enough that behavior is typical of a true behavior. It's not very strongly influenced by the periodic boundary conditions. Every solution that you find in a periodic boundary condition world is true in the whole world, but the question is how representative it is, because there is larger space of solutions. And what do you see? In these transfer sections, the little arrows are two-dimensional velocity in y and z. The red is giving you third dimension, so you have total information, and you see that the fluid is trying to produce some kind of vortices. So the red fluid, meaning top wall, is being dragged down, the blue is being dragged up, and there's some kind of rotary motion in this system. And then the midplane is very good because if you have turbulent motion, that motion will be crossing midplane. So midplane is a nice way to look at what turbulence does to the fluid. And now I'll show you what numerical experiment looks like. So now what we have done is we have started fluid from the random condition, initial condition, and we let it run for a while. This Reynolds number is a number where experimentally one sees only turbulent motion in the system, even though it's not very far from the onset of turbulence, which is around 300, 320. And what you see, I want you to look at it for a while. What you see is that the fluid tries to organize itself, and it looks like it's going to die to some simple solution. And then something happens, things explode, and it keeps doing it ad infinitum. So mathematically, one cannot prove that this fluid doesn't go into laminar motion. Laminar motion would mean that you just have parallel sheets. I'll show you laminar solution later. You just have parallel sheets of fluid and no turbulence at all. And in this world, it's very weird. It's true both of the pipes and planes. The laminar solutions always exist. So you can prove mathematically that the solution in which you have just sheets of fluid going like this exists for any Reynolds number. But if you're an engineer or experimentalist, either 1,000 to at some number, starting with Reynolds in 1880s, you only see turbulence.
Tell us again the geometry here. I mean,
So
are we in a co-moving frame or?
No, it's zero mean motion because top is going away and bottom is going toward us.
Yes.
So the experiment is done. There are two drums. There's a bunch of little drums.
Erase everything.
The experiments look like that. There are two big drums. There are four little drums. It's like old newspapers that you could look at how they print them. The plastic sheet goes this way.
Yes.
So it moves this way and that way, and the trick is to keep it stable and parallel.
Right.
Yes?
The laminar solution is stable also for any Reynolds number?
Yeah.
So there's
That's
no why you
amazing.
don't see it in experiments, it's just because it's a very...
Yeah, so now we understand in great detail. That's one of the reasons why we're working on this theory. Beautiful experiments were done in Manchester, the original place, by Mullin and Hock, and then in Delft, and now they're being done in Göttingen. So to make it, keep it stable, you have to make pipe which is optically perfect, to angstroms. It has to be 40 meters long or something, and you have to make sure that no truck passes in about 2 months when you're running experiment. And then what they do is, so they slowly increase the fluid velocity, and the way they do it is they do it by syringe. They pull the fluid this way in a big tank so it doesn't cause turbulence at the inlet. And after years of work, you get it up to 30,000. The next thing that you can do is you can now measure the perturbation of fluid, because in this pipe you can put little holes on the side, you can inject fluid to cause a perturbation. And then there's some prediction that perturbation should go like 1 over Reynolds number, and that's measured experimentally very well. What it means in dynamical systems language, yes, it exists, but it has very small basin of attraction. It's shrinking. So in any practical experiment, the imperfections of the walls and noise in the environment limits existence of that solution to about 1,000 or a couple thousand. That's what Reynolds saw originally. Now, the turbulent solution is here always, and that's the interesting one.
But when you, yes, right. So the two comments or questions here. The experiment is with no slip.
No slip.
And the simulation is also no slip? Or?
No slip, yeah.
And the solution is then a linear, the laminar solution is a linear shear flow, is that right?
Yeah.
Yes. And that one,
yeah.
and that one we know is
in pipe it's hard
linearly stable at arbitrarily high Reynolds numbers.
Yeah, there are two papers that prove it, and I don't know, for some reason some people claim the first guy didn't prove it, Romano, but I don't really care. It's proven for pipes and it's believed for planes, and now it's of interest to applied mathematicians because these guys like to bifurcate, so they like to take a stable solution and make it unstable. If they do this, they'll never find any turbulent solution. So it's only in 1990 that people found the first nonlinear solution, and they did it in some way that I will not describe here, but it's basically they stood on their head and they waved their legs and then got the solution. We don't do it this way anymore.
But you have subtracted out the linear shear flow from the picture here, is that right?
No, I think this is no.
You see the color, that's red and blue means right and
yeah,
left.
but this is a real velocity. I mean, it really means the stuff here is going that way.
I see.
So this is the true state of the fluid.
Mm-hmm.
For mathematical reasons, sometimes we subtract shear flow because then we have a vector space where when we have two solutions,
yes.
boundary but that's boring. That's not important for this general thing. So this is the phenomenon. So phenomenon is that you have seen turbulence, and you from now on will recognize it forever. Whenever you see this picture, you say, "Oh, that looks like plane Kuwait at 400. I've seen this before." But at no point have you seen this come back to itself. So there was no situation in which you've seen the same picture twice and any solution is different. So what's going on and how are you going to describe it? So that's the point from now on. Now, usually physicists will take a spherical curve, but right now it's not allowed anymore because we are talking to engineers and people who actually do fluid dynamic experiments. So from now on, what we will do, and this is accepted in the community, first we will study a situation where we make periodic boundary conditions smaller, the elementary cell small, and make sure that we still have turbulence at the same structure we are seeing, is the understanding that eventually we have to understand what happens when we extend it big. But we'll first look at the smallest representative of this behavior. So the smallest representative was found by Hamilton, Kim, and Molev empirically in the 2001, 2, some such year. And this is what now simulation looks in a box, which is big enough to fit 2 contour-moving rolls, whereas before we had 6, and that's already infinity for this kind of problem, because the correlations decay very fast between the rolls. And again, you're seeing the same kind of behavior. Every so often, the flow tries to organize itself. See, right now it's trying to just be 2 rolls, which you could imagine is a solution. It turns out there is no such stable solution, constant rolls like that you can prove mathematically is always the case. And then it falls apart and it keeps doing it for infinite time as far as we can tell. It never dies away. So that's the phenomenon. And what are we going to do about it? So now, here is the main idea. If we can find some exact solutions of Navier-Stokes which have this structure, we can give those names. So for example, the solutions I'll show you now have been found in Tokyo, Manchester, in Marburg, and Georgia Tech, and a few other places. And we all agree that these are the same solution, they're exact. And actually, one of them made it to the cover of, I'm sure nobody reads Physical Letters, right? But last Physical Letter cover is one of these solutions, actually, that I will be showing. And we all agree, we know, it's called E8, E7. We discovered it first, but these other guys published it first, etc. So we all agree on. So now the point is, if I find exact solution, give them names, I'll be able to start talking about what we see. I'll be able to name objects. And that's very important in Russian history and Russian history of mathematics. There's an orthodox sect of people who had a heresy of naming objects. And being able to name something is very important, and then we'll explain how they temporally relate. We'll start explaining dynamics in terms of things we can describe and we can predict. So what are the invariant solutions, exact invariant solutions of Navier-Stokes? The one that everybody who teaches fluid dynamics is this one. It's a laminar solution. What you do is you just say velocity goes from -1 to +1 uniformly as a distance from the center plane. You stick it in Navier-Stokes equation, and indeed it's a solution. So that's a laminar solution, has been known for 150 years. In 1992, Nagata, working in Manchester, found a pair of solutions which are exact. And I'll show you some more of these solutions before explaining what they mean. And here's a bunch of them. This was found by my graduate student Haukro, and the other ones are found by Gibson, etc. And we have now about 20 of these things. And what's the big deal about these solutions? You haven't seen anything like this, and it's very strange. The big deal is that this solution looks like a snapshot from the movie I showed you. If you look at individual video frames of what I showed you before, you will see this structure, you will see this structure, you will see this structure. You will see these pictures, you recognize them. But then steady, meaning that velocity goes all over the fluid like this, but if I put it in Navier-Stokes equation, it doesn't change in time. So if you put some ink into the fluid, it will move because tracers will move, but the velocity field, which is description of Eulerian description of fluid, doesn't change. So you have some totally convoluted state of the fluid, and it doesn't change in time. It's weird, and you haven't seen it before. Now, why you haven't seen it before? The next thing that they do, and that's what makes this, rather difficult subject, and will prevent some 10,000 physicists suddenly jumping in and doing it. You have to work very hard to compute stability of these solutions. So we compute the 30 linear eigenvectors of, which is, perturbations you apply to this fluid. And it turns out all these solutions unstable, meaning that if there is a little error in your code, you'll exponentially go away from it. So if you just run a computer, you'll never see it. And if you don't do it precisely enough, you will not be able to check that it's a steady solution. And this makes us solve this problem with ridiculous accuracy. So we solve it with every velocity field that you see here, we know it, all three components, with accuracy of 10 to the minus 11. So it's kind of physics clockwork accuracy. It's comparable to magnetic moment of electron, if you wish. But why would we do something so crazy? Because fluid dynamicists, engineers are happy if they get it to 10% or 5%, because they just have to get, properties of turbulence. We need to notice, so we are absolutely sure that we have found exact solutions, that they're isolated, our numerical methods converge to them, etc. And we cannot understand stability unless we do it very accurately.
But you are saying there's a finite regime of attraction for these solutions?
No, they're all unstable. They have no attraction whatsoever. Now what you can do is you can change the Reynolds number, and I've done this for Kuramoto, Shiroshinsky, but not for this problem. You can find really weird solutions like this which are stable. Just like laminar solution is stable. For very small Reynolds parameter numbers, they just happen to be stable. But it means that you have to control everything to the accuracy of 1 part in million. So there's no experiment.
The existence of the solutions is independent of the Reynolds number. They exist at any Reynolds number.
Well, that's a study. They exist for finite ranges of Reynolds numbers. So I won't show you the studies we do. What you do is you change Reynolds numbers, you change aspect ratios to make sure that they're robust and they bifurcate, they do this and that kind of things that solutions do in dynamical systems.
But you did say that you were talking about the laboratory. So can you actually realize such a thing even in the laboratory?
Yeah, so what happens in laboratories, and the reason why engineers are listening to us now is because in pipes, you can see them just like you could see them before. See, if you look at these pictures and then go to our simulation, you will see them in the simulation. So here is a simulation. And you will, stare at these two sets of pictures. You'll see that fluid comes close to that state, but because unstable goes away again. So now you have a picture. It says the turbulence consists, fluid is trying to do this, it's trying to do that. Every time it gets close to the state, it's actually unstable, so it runs away. So it's a picture of how chaos is created in dynamical systems. There is an infinite set of unstable solutions, so you come close to them, and I'll give you very nice illustrations later on what it means to come close to them. So they are there, and especially what's very striking in these pipes, you have traveling waves. So you have things that go down pipe for quite a while, and they are very close to exact traveling wave solutions, and they're experimentally observed. So that made it uncover of everything, science and God knows what. So that's why it's somewhat persuasive. Then the next thing that happens, you can say, well, okay, so you run a computer, you find some solution, and it's weird because it doesn't change in time, but I'm looking at turbulence. Turbulence, per definition, changes in time. So what does your solution have to do with my problem? So far, all I told you is that when you look at them, they look similar. But the next thing that happened was very impressive. It was done by Kawahara, assistant professor in Kyoto, and must have been like half a year in a dark room with a screen in front. And he found something I didn't think I would see in my lifetime. He found periodic solution of Navier-Stokes. Now I have to explain, I'll show you the movies, but I have to explain what it means. You have a volume of fluid, you set up velocity at every point exactly in this contorted way that I showed you. The thing runs, and 78.3 seconds later it repeats itself and does it for infinite time.
Is there a scientific method to do this, or is just?
No, we do it, we go to
You have to see
a mountain in California, and the gods hand them to us. But it takes like 2 to 3 years to learn the secret craft. And if you want to do it at home, what you do is you click on channel flow, which I cannot do because I'm not allowed to use wireless here. And just download it and run it at home.
No, but
Usually people call this science. I mean, if you can use equations, run them on a computer. And
no, but you have to like tune these things by hand, or there is a like.
Oh yeah. What are the methods of finding periodic orbits? I'll mention it. Yeah, that's what chaosbook.org is good about. That's what it's about. Okay, so let's go back to science. So here's an example. So now here's the solution. That the 75 time units in dimensionless form of Navier-Stokes just comes back to itself. So you start here, does something, and it looks exactly like a part of the video I showed you before, and then it comes back. Another one. So if I didn't tell you this thing is periodic, you would think, he's just running another turbulence simulation in a small cell, and you would never be able to tell that this is different than what you see from other ones. So what happens at some point, in the beginning, you know nothing, then you simulate, you see the structures. After a while, the human eye is not able to actually distinguish fine things about a structure. So the rest of the talk is how to really understand different solutions and structures, and for this you need a different language. This is physically very good to understand what you're looking at, but it's not possible to understand by looking at three-dimensional spatiotemporal videos. It's not possible to, figure out all possible states of turbulence, how they're related. So this is now for me, truly amazing thing. Now, you should just take a nonlinear dynamics course and try to find one unstable periodic orbit in 3 dimensions for Lorentz tractor, something that. And you'll discover it'll take you 3 weeks, no matter what you do, unless you just inherit a solution from somebody. So this just seemed impossible, because even, in 3 dimensions you have to get 3 numbers for a good guess and use some method like Newton method and so on. But this, 60,000 numbers and we get it right. Pretty impressive. So now, what are these solutions good for? Once you have a solution in this periodic box, it's actually a solution of 2 Navier-Stokes, because here's an example, because if you have it, it means all the repeats of this box are also included. So it actually solves the infinite Navier-Stokes. But it's the kind of solution that looks a little bit at what I show you in large simulation, because it has this structure. But of course, in large simulation, what's happening now is I've taken a solution because it's unstable. It goes into turbulent motion. So it starts as an exact unstable solution, but I'm not allowed to. That's something, okay, doesn't matter. Yes, I can restart it. So it starts as a repeat of a small solution, which I repeated 3 times here, 2 times there. And after a while it goes turbulent only because it has exponential instability. But it's exact solution on the other side.
Is it known if there is a way to combine these things, but to arrange the cells starting from the stable solution such that the whole thing...
No, stable solutions are useless. They're not stable solutions. All solutions that we're looking at are unstable. It's turbulent. But what one could imagine is that you could use different cells and glue them together to describe. Yeah. That, of course, is, I hope you join us, because that's what's involved in understanding spatiotemporal turbulence. How is it going to look at it? How do you think of very large systems?
And what about the periodic things, like the periodic solutions that you showed? Is it possible to glue those together to get a...
Yeah, Yeah, that's how you find longer solutions. I will show them first to people who don't know about this, and then. So, I won't show you this movie, but basically you can tell the difference between a periodic solution and a turbulent solution after all. So now the issue is this. In the beginning, we knew nothing except it was a laminar solution, and we could run computer. But now I have, let's say 50 different solutions. They're all exact solutions in Navier-Stokes. They all look like stuff you see in turbulence. So now what are you going to do? 50 different solutions. So you have to start understanding how to put this in one picture. How are they related, etc. One way is rather physical. Each solution, you can define kinetic energy because velocity squared divided by 2 is kinetic energy of a little bit, and you just add it up over the whole box. It's called kinetic energy. You can take the derivative of this, and you'll find that it changes in time by the power you put in here, so you can measure that for your solution areas in time. And then it gets turned into heat by dissipation through vorticity. So I'll just show you what you can look at as an example. So here is the energy you put in. The units are what it will cost you just a laminar flow. So turbulent flow is very expensive. See, the moment your fluid goes turbulent, it starts shearing a lot, and there's a great deal of dissipation in it. And if you are able to fly a plane without turbulence, it will cost you 1 gallon of gas per second, or whatever planes use. But because it's turbulent, it costs you 3 times as much. So changing an epsilon in velocity doesn't mean that you get an epsilon square root increase in cost. It's 3 times as much. Turbulence is a big deal. I mean, you just try to go a little faster, things go turbulent on you, and suddenly you have to pedal 3 times as hard to move at the same speed. So that's the meaning of this unit. Now, here is a dot. This dot is obtained by running a long time computer simulation. And now, depending what the waves are doing, you are putting more power in them. So you have to sometimes put more force to maintain the velocity. That happens here, or less force to maintain the velocity. And depending how twirly they are, you're dissipating more or less. So if it's very twirly, you're dissipating a lot. So that's a turbulent thing from infinite many dimensions onto 2 physical variables you can measure.
So one more time. D is dissipation and I is in what?
Power per square foot.
Okay, so both are energy input rates,
yeah,
energy rates, and this is a large scale, and this is a small scale.
Yeah, so the energy E dot is the I minus V.
Yes.
And here is the average. That's, the red dot is the average of the green curve that you run for a while. And now comes the amazing thing. The blue dot was computed on this first Nagata solution. So you solve for exact fluid once. You don't run it at all. You find this twirly solution which looks typical of the fluid, but steady in time. You compute how much energy you have to put into that one, and that's right there within a few percent. So knowing this solution gives you important physical information of a flow. It tells you what's the dissipation in the flow. And you don't run the computer, you actually think to do it, which is extra price, but sometimes pays off.
Maybe I can ask this also later, but there should be a time delay, of course, between energy input and dissipation.
This is steady state.
Uh-huh.
So the thing has twirled for a while.
But I thought this is a trajectory in time, no?
Yeah, but at every instant in time, you're putting so much energy.
Yeah. But then if you take this one time delay, one of the two.
Oh, you wanted to do time delay?
And then
you can do it. Yeah.
And then the circles should collapse to line.
I don't think so, but afterwards.
Okay.
I'll Skype you in 3 years.
Yes.
Okay, what's here in this? The same turbulent thing going on here, and now the same thing computed on 3 periodic solutions. What do you learn from this kind of picture? You find out that periodic solutions are capturing the global fluctuations of the flow very nicely. They're embedded in it. And You just have to do it for 78 seconds, not for a month, to get a number. And if you compute dissipation rate from these guys, it's now ridiculously good.
So what do you mean by 3 periodic solutions? I mean,
I showed you pictures of movies of 3 periodic solutions.
Yeah.
Now I'm showing you what they look projected in time onto input, power input versus dissipation. So that's
each
one way to
individual-
visualize.
So each color is one of the
Yeah, there are 3 periodic solutions, they're colored different. So now, so that was just kind of motivational, but we have a much more, impressive scheme of visualizing energy and power. This is traditional in the community. So what we do is, we actually go to infinite dimension fearlessly and project from it in such a way that human eye can understand what's going on, even though we are in infinite dimension. And I'll try to explain the main idea. It's rather simple. The fluid dynamics is a natural energy norm because there is a kinetic energy. So that means there is a thing that if you square it, so this u comma u means I square the velocity at every point and I integrate over whole volume and I divide by the volume. So this is mean energy density. If you have that, then you can define a norm between 2 solutions, and you can discuss how distant are 2 solutions in fluid dynamics. What you do is you dot the velocity of the 2 solutions, and you divide it by the volume. So this is a vector norm. That means that now we can, instead of looking at our 3-dimensional space, we can look at 60,000 dimensional vector space, and we can dot states in between states. So here is, for example, how you do it. We noticed that this Nagata upper branch solution was a pretty good representative of dissipation and viscosity of the flow. So let's see how often flow comes close to this solution. So what we do is, you take this solution, and now, this is problem with symmetries, because if you flip the 2 plates and reverse the velocity, that's also a symmetry. And if you flip them this way, that's a symmetry. So there are 2 discrete symmetries. So we can take the solution and we can flip it 2 ways, gives us 4 different solutions. And they're all exact solutions of Navier-Stokes just by symmetry, by invariance arguments. But they're very distant from each other in state space because they look different. Velocities locally all look very different. And that gives us a 4 basis vector in the 60,000 dimensions, or infinite many dimensions. They're just obtained, they're orthogonal just by symmetries. So for example, if we add them up, we get something that's kind of average velocity of 4 solutions. And then we get 4 basis vectors. I plotted them here in the coordinate spatial 3D representation. And now we can look at state of the fluid. So here is the turbulent state of the fluid, and dot it with one of our basis vectors using that norm, which means velocity at every point is dotted by integral over the volume, and see what it looks like, what happens in this coordinate 3. So now, out of 60,000 dimensions, I've taken 4 preferred coordinates. They're chosen by physics. There is a preferred solution. So this is not some 7th Fourier model. And this is a solution, and I'm comparing this solution to another solution.
But they have to be in sync somehow, right? They're both time dependent.
No, I'm using invariant solutions, so that's not time dependent.
One is time independent, yeah.
But this one is independent, time independent basis, and this is the time dependent component seen from that.
And this solution
component.
is time independent.
This is independent.
Oh, this one is, okay.
Because it's constructed from invariant basis. So that's what's nice about having these exact solutions, and that's why it wasn't done before, because we didn't have them before. We didn't think this way before. And now, amazing thing happens. So this we call Starship Enterprise. All the solutions that I've shown you, many more that I haven't shown you, now sit in a one big family. And for example, laminar solution is this dot here. The Nagata upper and lower branch is this one, and upper branch, forget why they're called that, but they just have some random names, historical. So this one is more turbulent, this one looks almost laminar. There is a Halcron newbie or new branch, And then, we have 20 more of these things. And now, every line here, you might be very blasé about this picture, but this picture has 1,000 videos in it. Because every line here is a computer simulations in 60,000 dimensions, so it's a video. So what it says is,